overview of what exactly is the geospatial modeling techniques are there. There are different classes or classification of those, and then few examples. So that's the topic which we are going to cover today. So the content which we have thought of covering today is that what exactly is the spatial analysis, then what a spatial analysis model represents, then spatial model as a tool, so how we can use different spatial models for uh, carrying out few activities, as well as there are different kind of spatial models are there, so few classifications we'll see, and the final examples of these spatial models. So let's say that why we need a spatial analysis. So generally in any kind of spatial environment, we look for a kind of spatial pattern. For that pattern, we need to have an understanding of how the different features or the component within spatial domain interact with each other. So there's a very famous Dr. John's uh, uh, cholera discovery paper is there, and it shows that how the simple representation of the data set has led to find out like why the how does the cholera disease is actually a waterborne disease. So this was established using a simple representation over here. So this is a famous example of doing a spatial analysis. So over here we see that there are number of wells, and these are tube wells from where the water is being used for drinking purpose. And there is a one specific well. Around that, the number of cholera deaths in a different areas was reported. And so based on the interaction which these people are having, so it means like they are going for drinking purpose, they are collecting the water from these particular two wells, and they have been suffered. They had been suffered at most, and due to that, it was established that there is something related to this tube well, and later on it was discovered that the cholera, actually the waterborne disease was cholera is actually waterborne disease. So this is Dr. Snow models which he has created for showing that how the public water pump is being related. So the basic objective of any spatial modeling is that we study the different kind of interaction between different features, and then we also try to do a kind of predictive modeling. So generally, the major two purpose of these spatial models are there, that either we try to understand what exactly is the underlying patterns, so that comes under the descriptive modeling. So under that, we look for a kind of that is there any specific cluster around a point, or is there any specific similarity between the different features and that are actually co-located. So there's such kind of information is extracted under the descriptive modeling. Where in the case of predictive modeling, we first establish a specific features, understanding of a particular features, or maybe the spatial interactions which is taking place at one place. And then based on that, if it is having a temporal component, then we look for a kind of prediction in the future. So considering the what exactly is happening in the past, based on that we do an estimations. So if you say that the spatial analysis is generally being used to find out the different kind of spatial interactions, and under that we do a study of finding out specific patterns in those. So those are called actually descriptive modeling. And then we also use the identified patterns to do a future based prediction if your model is having a temporal component, so we can do a future prediction as well. So if you see what exactly is the spatial model, or in any cases, as we know that basically models are a kind of abstract representation of real worlds. So what we do it in case of spatial models, we identify different components of a specific process, and based on that we create multiple layers. So most of the information which is not relevant gets removed from the actual world, and only the essential or the important feature which we think is important for spatial interactions are being taken. So those are basically a kind of raster or vector layer that is being created, and those raster or vector layer are then used in tandem based on few mathematical relationship or statistical relationship to do or to define a particular pattern or interactions, or maybe we can also use the for creating future prediction maps. So that can also be used in case of a spatial model. So generally in spatial models, the important components are that you should have essential features which you think will be important for your modeling purposes. So all the input layer or the input data should be extracted, and it doesn't represent each and every real world features. For any modeling process, we ignore most of the variables which are not directly linked to our modeling requirements. So all those layers is being removed. For example, this is just a map which represents a single snapshot of different features on this map. So we see that there's a lot of complex representation. There are a lot of road networks, and then we are also having residential areas, and there are a lot of few interaction places or the ROA, AOI places where the people come and do some kind of interactions. In case of representation, we only have only the road networks and the few important places which are essential for the modeling purpose that has been created. So this is kind of a simplification of the real models which is being done. So first, our objective is always to create a data set like this, and then on these simplified data sets, we build models based on our understanding of different interactions. So this is just a simple example where we need to find out which is the best route from different multiple paths. So this is basically a shortest path problems which can be used to solve this problem. And for that, we need to have a road networks and corresponding cost function or the cost associated with that. In case of, if you see the basic purpose of any spatial modeling is that we need to find out a specific spatial phenomenon or pattern. So generally in those, we also look a kind of interaction within the layers. So there may be cases that we may be interested in how does one particular feature is actually impacting the other feature. So going back to the cholera examples, so there are two different features which we see. That the first one is the location of the all the different people who have died due to cholera disease. So that was the one input, and there was also another layer related to the different water pumps, the public water sources which was there. So that was also being represented. So one way of doing or trying to find out the modeling purpose is that we can look for a kind of cluster of different death which has happened. So generally, if you do a kind of interactions, then we will find out that there is a centroid located at a specific locations, and based on that, we can say that all these diseases are actually having something in common. All the death are there is something common at, and that is located at centroid. So that is basically only taking the death of the death locations or the peoples who have died, that location clustering we are taking into an account. But when we try to link that to a specific source based on the information available that each of those deaths or the houses, the actual source of the water. So if we link based on that, then we are looking for a kind of interaction between the death and the corresponding source of water. So combinations of these two is possible, and based on that we can find out that the two different layers are actually interacting. So once we have that, then we can build a kind of different process model. So generally, in case of process models, we'll be having multiple features which may interact with each others. So most simplistic example which we use using GIS tools, like finding the suitability place. Maybe it may be a suitable landfill places, or it may be to find out the best suitable place to put a new school. Something of that kind of problems can be defined under that. So under that we will have a few variables which will say that the schooling, if you want to have a school, then it will have a specific catchment area. It should be accessible easily from the road network and so on. So we can define a set of parameters, and that can be used based on the layer available to create a simple suitability modeling. Where in case of distance modeling, we can have a multiple models, or which may have multiple routes, and based on the cost, so either it may be a fuel, the length of that distances, or it may be the time it takes. So based on those we can do a kind of distance modeling. Then there are few cases which may arise in, like there may be a few eco-sensitive areas, so that those areas needs to be avoided uh, for any route finding. So those kind of problems comes under the distance modeling, or those are also called network based modeling techniques. Then we have very specific problems related to in specific domain. For example, the hydrological modeling. The basic purpose of hydrological modeling is that find out the rate at which the groundwater is getting recharged. So, and or maybe the time it takes for any particular dam it breach. So what is the time available at the downstream, so that the time lag can be studied, and that can be provided as an input for in case of disaster management cases. Such kind of things we can do in hydrological modeling cases, where in one case we are seeing that the ground recharge, there are a lot of layers which will be interacting and then providing the input, where in case of suitability map will have static layers, and they may be considered to be interacting with each other independent of the time domain. Then there are also a lot of surface level modeling which can be created in at different heights from the surfaces, that can also be modeled. So it's called basically a layer based modeling and so on. So process modeling, the spatial process modeling can under that we have the interaction between different features, and that gets created under the this modeling process. Then the spatial modeling process can also helps in identifying or carrying out for a few places the missing data values. For example, let's say that we want to find out the concentration of metals around a riverbed. So if you do a sampling, so you'll be only able to get a measurement at a specific places. So those may be a point based measurement. So depending upon your area, you can take 50, 60 or different points, and we can measure the concentration of different metals around the river channel. But if somebody says that using those data sets, try to find out how the concentration around the river channel is available. So in those cases, we need to do a data filling. So that is possible through the application of interpolation. So spatial process models can also help in identifying different process modeling, and based on that we can do a kind of interpolations to do data filling. So in nutshell, if you see that any kind of spatial models will require a kind of data representations, or those are actually the input which is required for carrying out spatial modeling. So like in this case, there are a lot of layers which is available. So hydrological, topographic, land use, and then administrative boundaries, the kind of soil types, and so on. So these models, these different layers has to be extracted from the real world, and then these layers can do and may have some kind of interactions. For example, under the hydrology, the rate at which the water get infiltrated into in a particular area has a dependency on the soil layer. So if soil types or the soil density actually makes important uh, part that how much water will go or sip in inside. So the soil type is one of the input parameters. Similarly, the precipitation is also dependent upon the kind of land use. So if you're having vegetations available on open ground and it is covered with the vegetations, then there's a high chance that water will be going inside. But if you're having a concrete or maybe in the road networks, a road, so the water cannot seep in. So it will just flow on the surface and then finally it will get merged to the drainage channel. So if you see the how much water will go inside ground is a kind of is dependent upon the land use, the kind of soils, or there may be some other parameters related to the soil and so on. That is also dependent upon the rainfall or the precipitation rate. That is also one of the important parameters. So we see that to do a modeling, we need to first understand those relationship, and then we also need to look for a kind of interaction between them. So we have to carry out different experiments. So and based on that, we can derive a few empirical solutions, and that can be used to do kind of modeling. So that's a kind of one of the way to do a simple modeling based on empirics. So if you see in this case that we are having a set of input layers, and then we also need to have a kind of interaction among those layers. And if you study such kind of interactions, so those models actually falls under the category of simulated or the process model. So those are actually related to the process model. So there are a lot of softwares available, like in case of hydrology, we are having a weak models. If you want to find out the land use changes, so there are a lot of land change modeling softwares are available which can be used. Or sometimes people writes their own custom models based on the understanding. Like in case of ecological studies, where prey and predator relationship can be identified. So which gives the kind of maximum and minimum number of populations present at a specific place. So there are a way to define those interactions in terms of mathematical relationship, and that helps us to create specific models for specific applications. So if you see, so we see that if you want to do a study of any specific or spatial features, especially over here we're talking about the earth-based features, then we need to have a representations of that model. So we need to have abstract models of the real world, and these abstract model represents all the layers which we think will be important for our modeling. And then and based on that input parameter, we provide it from the real world. So let's say if we see that hydrological modeling it requires soil as an input, so we need to do a kind of study and at a particular location, and we need to provide the kind of soil type as an input to the models. So that from the real world we get few observations, and those observations are actually inserted into the model input, and finally we get some output, and these outputs are again getting compared with the actual output. So if we see that if you're studying a ground discharge table, so in those cases we will find out the soil type, the land use land cover type, the precipitation rate, and so on. So after giving all those input to models, it is going to give us an output, and then we need to do a kind of validations of those outputs with the real world. So this cycle continues till we reach a proper of our results. And these observation also helps us to sometime it may be possible that we may not have an understanding of actual process itself, rather than we only see the input and output as a whole. So in such cases we can form a few hypotheses by simply building models, and that hypothesis gets we do a testing of that. So basically it's an experimental model which we build it, and then we validate that hypothesis. So models help us to form a few hypotheses based on the observations, and then using those models we get an output, and then we validate that output with the real world to define a particular process or phenomenon at an on an earth surface. So that's why we also call different models as an analysis tools. So let's take an example of the category of models which is called spatio-temporal modeling. There are different ways of defining the spatial temporal modeling. So if you're having a particular area, so let's say that we want to maintain a sustainable growth of a particular forest areas. So in this case, what will happen is that we need to do a kind of forest management in such a way that we should have an appropriate number of different woods or the trees available in the areas at a different stages. So there may be a cases where just logging has happened, or there may be places where few years back a few new trees was grown, and some places we may have a large number of trees grown, and so on. So if you're looking for a kind of specific purpose like how to do a forest management, in those cases whole area is considered to be filled of a particular types, the forest type, and then we are only interested in the different stages of those trees which is available in this area. So it means that we are only interested in the attribute values which is available at different locations. So this can be done using simple prediction models. So we know that each of those tree will have a specific growth rate, and we know how much time it will take from sibling to a full grown tree, how much time does it takes, and what is the last time when this particular area was logged in. So based on that, on the time evolutions, we can see the overall status of the total forest areas. So in such cases, what happens is that we are having a same rules, that is the growth rate is being applied at all the different locations. So generally these kind of analysis is being carried out in a raster or the grid format, and within that we will be having only specific rules, and within that grid we assume that whatever is going to happen within that grid, that will be the major factor for defining the processes. We don't look for any kind of interaction that this grid will have an impact on the neighboring grid, or it means that the forest at one location we are assuming that will not impact the forest available at the nearby areas. So this is a simple models which is also called simple evolution models, which is a kind of simplistic model of the temporal modeling. Later in this case, what we can also do is that we can bring slight amount of complexity as well. So in these cases, we are not we are still working in at a particular grid level, but we are taking input of all the layer of features in that grid. In this case, at a one particular attribute, that growth, the tree growth rate. Along with that, we also take an input for other input variables. For example, how much rain is going to happen in that particular areas, or how much sun is available in that areas, and so on. So in this case, we see that within a simple grid, in a particular grid areas, we are interested in to find out the growth rate of a forest, but we are taking input not only the forest type or forest categories, but we are also taking input for other factor which is actually affecting the growth rate. So those are actually rainfall, the sunshine or the albedo which is available at a particular grid, and so on. So that can be created, and such kind of dynamic interaction within models can be created. In fact, in few of the cases, we may be interested in having a different kind of models for, let's say, grown up trees, or there may be a cases where if the tree stage is at a sibling stage, or maybe at the uh, not completely mature trees, that is the state. So in these two cases, the rate, the impact of all these different factors may be different. So that can be taken in. In nutshell, we can say that will be having a similar kind of models, but depending upon the state of main input features, the output gets changed, and that's basically helps in creating a dynamic interaction. So we take the different input parameters and interacting parameters into the modeling environment, and then based on that we carry out the activities. But in this case also, it is very clear that the impact of this particular land piece may not have an impact on its neighboring area. So this assumption is still hold in this case. Then there are slightly modified versions. What we do is that is called a coupled dynamic systems. In this case, it is assumed that whole area is covered by lot of different factors, not only the kind of the type of particular feature, like in this case the tree or the forest areas. Along with that, we also look for the interaction at the neighboring areas. So it means like the amount of trees, if you think has some kind of relationship with the distance to the river, so that can also be taken. So it means that distance to this particular river can have an impact on these tree clusters. So in this case, we do kind of study the interaction between those neighbors, and based on that, we can create a model for a particular grid. And so this is again taking into a simple modeling approach. Again, interested only we are giving a only growth rate. Sometime it may also be happen that we may be interested to have a combined coupled effect, and that's we call it the multiple subsystem models. So generally in this case, what we do is that we take the tree's growth, how it is getting impacted from its environment, and as well as the number of tree or grown in this area may again give a feedback to the kind of land use, or maybe the precipitation which will happen in a particular areas. That can also be modeled. So in this case, we see that there are a lot of coupled models. Not only the growth rate of the trees, that's one model, but along with that, the impact of those growth is how is that the growth of a particular forest area is actually linked to the overall environment. So how it is linked to a precipitation, that can also be taken in. So in this case, we are having a multiple models working for different features in a specific areas, and we also take an interaction between the grid cells. So that is also being taken into that. So this is being considered to be most complex system. So generally the overall climatic system will have a kind of such models, where we can have a biosphere models, we can have ecological models, we can have hydrological cycle models, and all of them can be combined together to define uh, the actual the system, Earth as a system, and how it works. That can be models, and people are trying to build such a small coupled models for doing an Earth level simulation and modeling. For model as an interpolation or extrapolations, there may be cases like we may be having a few input values in our studies areas, and then we need to find out the values at different places. So this can be modeled with the help of a specific mathematical relationship, and that's basically in this case the only distance based and variable values is being created. So there are variogram concepts comes in over here. So the geostatistical tools is being used to identify or create to define the interactions of the different variables, and these are also called regionalized variables, and based on that we can do some kind of interpolations to fill all the gaps. So that's what is being shown over here, that we are having a few known values, and based on that known values we compute the values for all the areas. So this is just an example of the places where different metal concentration is being taken at a river side, and these are basically a flooded region. So once in a season the whole area will get covered or inundated by the river water. So the water will get spread from actual main channels to its own side banks, and again it will recede back to the main channel. So this process continues for years, so that the continuation of that process basically leads to different kind of concentrations of heavy metals. So that can be there. So the places where we will have a frequent flood, or the frequency of flood is quite frequent, will be having a large number of, or the concentration of heavy metals will be higher. But as the frequency areas where the flood or inundated locations are lesser, so it means at one particular place, uh, out of 10 years, let's say only 2 years this area gets inundated, where these areas actually gets inundated at approximately 5 times, then the concentration at this place will be higher compared to this. So such kind of relationship can be built in, and based on that we can do a filling of all the areas, and we can create the concentration of the heavy metal in those areas. So such techniques are actually called the extrapolation of these data sets, and these are the job of variograms models, which helps in Kriging is one of the examples which uses variogram as a tools to identify and to basically do an extrapolations to fill the values from unknown locations. Sometimes we need models to quantify non-measurable values. For example, we may be having the temperature measured at a particular location. So that basically gives the kind of temperature or daily temperature at a particular locations, or year wise. So this is just an example of year wise temperatures which has been recorded at a particular place, and then these measures in a longer durations are being used to define the kind of rate. So generally the rate of change of temperature, or the anomaly of temperature from its mean values, cannot be measured directly. So if you want to find out how the temperature of the total Earth is increasing day by day, or maybe year by year, what is the rate at which the temperature is increasing? So in that case, we need to have first all the observable values of our temperature at different years, and then we do a kind of simplified mean fitting of these models and to get a kind of rate. And that again we can do a fitting from different ways. There are different models which can be used to identify these uh, rates, and these rates can be used for further modeling to do a feature modeling, like what may be the cases after 10 years or 15 years, what will be the temperature in the near future we expect. So this quantification of such things like density or the concentration or the rate which is not measured are actually can be created based on the density or concentration measured at a particular locations or a particular areas. So that quantifying those such kind of non-measurable uh, uh, parameters is possible using the models like this. So this is just an example where temperature anomalies based on the rate determinations can be done based on the either using a linear models which shows that it is increasing at a specific rate, or we can have non-linear model as well as to define a given upper and lower limit of the temperature anomalies. So this is again is used in climatic studies to identify how much temperature is changed in the last few years. So if you see that the kind of spatial models which we look for is can be categorized based on the time scale. So it may is it the model requires time as an input. So we may be having time scale which is a discrete in nature, or there may be a continuous time evolutions, or there may be a cases that the models may have the modeling or the formulas or the interaction which we have thought of between different features. So is those features interaction is static in nature, or is it like dynamic? Does it evolves or keeps changing depending upon the state of the features available in a particular grid or in a location areas? And then we also have a few models which is completely deterministic in nature. So it means like there are well defined equations, and that equation actually determines the what will be the outcome. For example, the precipitation at a particular area is a well defined function of pressure, then the wind speed, the kind of temperature, and the amount of moisture available in the area, in the air. So there is a fixed formula or relationship based on the energy conservation and the mass energy conservations that we can define a set of equations, and that's actually called a deterministic models, where in some cases we use the stochastic model, which is nothing but taking measurement at a specific places and then deriving it or doing a statistical analysis to do an appropriate estimations of a values. So we are having a different dimensions, like does the rules gets changed. So it's a static and dynamics, we can say. If the rule is fixed with time, so then that is called a static nature, or if it is the rule gets changed with respect to time and as well as the state of values at a particular grid. So those are called actually dynamic systems. We are working in a discrete time interval, or we are working in a continuous time interval. So that's the another time scale. And then we are also having the way the interaction is being defined. So there is it a deterministic model or it's a stochastic relationship which has been identified. So based on that, we have different kind of spatial models, deterministic and static models. In fact, map can also be said as an deterministic static model, because it just represents the snapshot of different features available at a particular time. So that's completely static, and deterministic because we have already identified that what is road. So there will be a few set of rules which will say that what is road, what is house, what is residential areas, and accordingly the categorization of the spatial zone will be done. So that's the kind of deterministic and static kind of models. Where in case of stochastic data sets, we use the multiple measurements taken at different time stints or different places, and they gets combined. Spatial interpolation is a kind of technique where the stochastic techniques is being used, and there are stochastics discrete time space. So these are basically the model which is being used widely in land use or the queuing theory or pedestrian management cases. And these are basically a Markov based system which just says that the impact of the current output of any system or model will be dependent upon what has happened in the previous time epoch. So such kind of things can be built in, and this interaction can be will have an complete discrete in nature. So the interaction will always be happening a particular interval. Sometimes these same things can be elaborated and can be created a continuous time space, and the spatio-temporal modeling is being used for such kind of process, like UF analysis is again one of the example where uh, identification of different spatial phenomenon and then stability of different phenomena can be studied. So if you see that currently there are a lot of different tools and techniques are available, and there is not a single software or a GIS software which is available which will provide you all kind of geospatial modeling techniques. In fact, these geospatial modeling techniques are very unique to a specific application areas. So accordingly, we'll find there are a lot of different tools and algorithms available which allows to do a kind of interaction between different geospatial phenomena. So there's no integrated geospatial solution is available. Rather than most of the time, the geospatial modeling, if you want to do some kind of advanced geospatial modeling, then you have to convert your geospatial data outside and convert in a specific format, and then you have to carry out that modeling outside the GIS environment, and then after doing a modeling again we have to bring it back to GIS environment. So based on that, we have a lot of different modeling tools, and those modeling tools works on spatial statistics, or there may be spatio-temporal models are available. Spatial data mining techniques are also being used. Geostatistic, as I said, is used for interpolation and extrapolations of the cases. There are a lot of multivariate analysis where we look for different kind of layers and interaction between them, or a combined effect of all those variables. Let's take an example of the landslide. So if somebody wants to do a landslide hazard zonation and of a particular area, then landslide, if you know that there are a lot of factors associated with that. So any places if landslide happens, landslide may be dependent upon the kind of slope of that particular area, the amount of rainfall which will happen at that area, the kind of soils which is present, the kind of land use, and so on. So there may be a multiple factors which we can take it from based on our observation or from the literatures, and then combined effect of all those can be studied using factor analysis or PCA. Such kind of tools can be used to do a kind of multivariate analysis to do such studies. There are also geocomputational models which are now which is basically using a kind of agent-based models. There are machine learning algorithms are now being combined, like SVM neural networks. Then we are having deep neural network are also coming in and playing an important role to find out the different geospatial geocomputational method which falls under these categories. There are few fixed algebraic, so it's a method which is nothing but a kind of deterministic and static in nature. The spatial relationship may be also maybe having an autoregressive in nature, so it means that the interaction at one grid will have some kind of impact on its neighboring areas. So that relationship is being exploited over here to do a spatial autoregressive modeling, and that's what and all these tools, there are different tools which allows few of them to carry out in that environment, and we can choose based on our requirement the kind of methods to do a geospatial modeling. So just take an example of how does the geospatial modeling is being done. So this is just an the land use, land cover change modeling tools which is being built in IRS. So over here we see that it provides a provision for different years land maps, so that can be provided. And we also require a set of drivers which we consider to be an important, which will derive the changes from one land use or land cover to another land use or land cover. So those drivers, we do a selections, and based on the different relationships. So as we have earlier seen that there are a lot of techniques are there. So based on the logistic regression or the multivariate regression techniques or the neural network based regression techniques, we can look for a kind of relationship between land use and the corresponding drivers. And based on that, we can do modeling uh, for the land use pattern change, and that can be used to do a future prediction as well. So these tools has a kind of input which is nothing but a kind of data input for the two different layers, the different layers for a particular area, so that can be provided. Then the kind of modelings, as I said, like you do we think that the interaction between the different drivers and the corresponding land use is actually a logistic based regression or a linear based regressions? So there are different methods which can be selected, and then we provide the base year drivers, and we based on that we look for that if the relationship whatever we have established, is it possible that based on if that status quo continues, that relationship still exists. So how does the land use pattern will look like maybe after the next epoch or next durations. And then this also have a few accuracy assessment and help and tools to a simple visualizations tool which helps us to do a kind of output display. So this simple modeling tools combines the geospatial data as input, and then based on that it also provides the kind of predicted future maps from which can be used for doing a planning and so on. So the few features of that software is that it provides a logistic linear regressions kind of interactions which is possible, and this is also possible that given in a base year driver we can do a prediction for the future years, so that's possible. Then there are a few the policy inclusion which has been created, so we may have a kind of restrictions, let's say as per the government rules that all the forest area has to be conserved, so the change of forest land will not be in any other time. If that rule exists, then how, so that we can provide that kind of input to the models, and based on that it can do allocations and the corresponding maps can be created. There are also a few places sometimes we don't want to do a specific modeling in specific areas, or sometimes we are interested in to carry out only study in a particular areas. So that's kind of mask and OA selection provision is also there. Then we can also look for demand driven allocations. What does it means is that let's say that governments decides that in the next 10 years whatever urbanization we had in last 10 years we have to double it. So if such kind of things happens, then it means that there is a uh, there are new fresh demands for the urban area will get created, and if that exists, if that gets created, then what will be the impact on the overall land use or land cover pattern in a particular area? So such demand driven input as a part of policies can be provided, and it is having a few tools to carry out maybe in a command based or GUI based or any different formats are available which can be used for carrying out the land use land cover modelings. This is just an example of the input, and based on the input output, the corresponding growth rate for a particular area has been predicted, and this has also been validated. So this is just a one the input. So there are a lot of different studies is being carried out using this model under the ISRO IGBP projects, and quite a good result has been published based on these outputs. Similarly, we can also have dynamic simulation models. So these are the two examples which I have picked up from the Earth science model of NetLogo. So over here we see that in this whole area, this is considered to be a kind of forest area, and this forest area is having a corresponding fuel load. So fuel load is nothing but the amount of dry fuel which is available in a particular areas. Now, let's say that our job is to identify if any fire happens at any one of these locations. So, is it how does that fire will spread? How much forest will get destroyed? So, if such kind of questions needs to be answered, then that is not possible to carry out that experiment in real world. Rather than we have to do a multiple simulations based on our understanding, and then we can come up with a specific parameter. So forest fire models can be used to identify those. I'll show the how the limit or a particular the fire the fuel load factors can be determined based on multiple simulation. Similarly, this is another example where a simplified climatic model has been shown. So over here we have a different parameters like the cloud which is present in a particular area, or we are having the amount of CO2 concentrations. So as a modeler, we have provisions to increase or decrease the cloud presence in this area, or the kind of the CO2 concentrations we can manipulate. Along with that, we also have parameters to control the albedo, the earth albedo, and the sun radiations. So giving these four input, we can do a kind of simulation for overall temperature, average temperature in on this surface. So this is showing a large time epoch result. So it started when simulation starts, it reaches as a steady state. Then as we increase the number of basically the cloud in this area, the temperature goes down. Then if we increase the concentration of CO2 in the same area in same modeling environment, then we will see that there will be a rise in temperature, and after some time again there will be rise in temperature. So generally, if you see that we have a kind of environment where we can do a multiple simulations and create a different scenarios, then we can also do the kind of simulation node which is not only in the linear in natures rather than stochastic in nature, and having a long-term average which can be computed. So such kind of dynamic simulation models are available, and that can be used for generating different simulation environment. Coming back to the forest fire, where the parameter extraction I was telling. So in this case, what has been done is that around 1,000 times this simulation was carried out, and with a increase in fuel load. So the fuel load got increased like every 10% has been increased in from 0 to 100 times. So this is a total fuel load. So it starts from fraction of fuel load is from 0 to 1, and then for each of those cases again 100 times the simulation is being carried out, and based on that we try to find out how much forest gets destroyed. So if the fuel load is lesser, the amount of forest fire of the forest which will get destroyed will be lesser. If you increase the fuel load, the forest fire will destroy the larger portion of the forest area. So this process or these systems can be simulated, which gives the kind of range for each of those areas. So you see at for the lower fuel load, there are very less amount of forest fire which is destroyed, but as we go it maybe around 50 to 60, if we start increasing, then there is a larger chunk of forest fire gets destroyed. But if the cases where we want to look for that, if the fuel load is let's say 60, in this case it comes around 68% of the total areas, then the chances that whole forest will get destroyed is quite high. So such kind of simulations can be carried out that at a particular break-in point, after that there's no chance of getting a complete forest preserved. Such kind of simulations where we can carry it out multiple times, and then the statistical analysis can be done to arrive a parameter like what is the optimum forest for fuel load which as a forest management people can maintain, so that there's the least destruction of the forest area which is possible. This is another example where the modeling can be done. This just shows the with the time there are a lot of vehicles which travels on a road, and this road is actually having in between a rail bridge. So if you want to find out that how much average time one particular vehicle takes from starting from these locations to these locations, what is the average time? So that is being shown on this plot, and as so this is the time duration which is being found out, and this duration time duration is basically the function of the kind of vehicle which we are having in this area. Along with that, we also look for the rate at which the vehicle being introduced in a particular road, and we also can do a simulation that at a particular frequency that this railway crossing gates can be closed. So if we combine all these three factors and all of them will be acting independently, then we have to find out an overall average time of a travel, and as well as the number of vehicle which is present in a on a road. So if you want to find out such kind of aggregated results, so these are possible using a simulation tool called agent-based modeling tools, and this is being just shown that when the gate is open, and if the rate of the vehicle type and number of vehicle which is of a particular type is fixed, then we are having a specific number of vehicle as the frequency of the vehicle gets or the train gets increased, the corresponding same the number of vehicle is now on the road is increasing. So this is kind of simple limitations can be identified. We can see that how much this road can accommodate the additional vehicles and so on, and that can be used for traffic management and so on. So we see that there are tools available which can be combined together to come up with different spatial models to define a particular spatial interaction of the process, and which we can also do a kind of predictions and as well as understanding of underlying processes using geospatial modeling tools.